this is x3, past exam 3, question number 33. And here we have a naive Bayes, and we're treating it as a Bayesian network. So that's a special case of Bayesian network, and the question is asking for the number of conditional probabilities we need to store in the CPT, conditional probability table. So let's first draw the Bayesian network. So it's Y as the parent, and there are 4 features, so 4 axes, so x1, x2, x3, and x4, and each one can take on 6 different possible numbers, so let's say 1, 2, 3 until 6, and the same for the other ones. And there are 3 classes, means Y can be 1, 2, 3. So that's the Bayesian network, and we need to compute the number of conditional probabilities. So the first group of conditional probabilities we need are the prior probability, what we call, so basically the probability of Y being 1 given the parents. We don't have parents. I mean, Y does not have a parent, so it's just itself, and we need that. We need Y, probability of Y being 2, and the thing we don't need is probability of Y being 3, which can be computed as 1 minus the probability of Y being 1 and minus the probability of Y being 2. So we don't actually need this, we only need 2 so far. So far we need 2. Okay, so now let's move on to probability of x1. So again, by definition, the conditional probability table, they are the conditional probabilities of each variable conditioning on the parent. So axis 1 needs to be conditional on the parent Y, and Y can take on 3 values, so let's start with 1. So we need this, and we need x being 2, and we need 3, 4, and 5. And for the similar reason as Y equal to 3, we don't need that because it's 1 minus the other ones. The probability of x1 being 6 given Y is 1, this can be computed as 1 minus the other ones. So let me rewrite it in this way. So sum of x is 1 to 5. Probability of x1 is x given Y is 1. So we have all of these in the table already, so the last one can be computed. So far, given Y is 1, we need these, and there are 5 of them. Okay, that's only given Y is 1. Y can be 1, 2, or 3, so naturally we need to multiply it by 3. And x2 and x1, x2, x3, x4 are completely symmetric, so there are 4 of these things, and they're independent of each other, so we multiply another 4. So the total number of things we need to store is 2 plus this 5 times 3 times 4. Okay, so one thing that we need to be specifically careful about is, can we compute the probability of Y is, say, 3 given Y is 1 and Y is 2? So the question is, probability of x is, say, x is 1 given Y is 1 plus probability of x is 1 given Y is 2 plus probability of x1 is, again, 1 given Y is 3. Sorry, Y is equal to 3. Would these 3 probabilities sum up to 1? If so, we don't need to store anything given Y is 3. And the answer is no. These do not sum up to 1 because they are conditioning on different things. Conditioning on each one of these, we have a probability distribution. And the probability distribution means the sum over all possible different values will be 1. But here, there are different things. There are different distributions. So when you sum them up, you don't get a 1. So no, we cannot do this. We cannot compute the conditional probability given Y is 3 based on the ones given Y is 1 and 2. So we do need this multiplied by 3. So this is not 2 in particular. And the next question is actually computing joint probability. A is 0, B is 1, C is 0 for a Bayesian network. So let's draw it again. So the y value is V here. It's binary, can take on either value 0 or 1. And then there are 3 children, A, B, and C. And all of them are also binary variables, so they're all 0 or 1. So that's our Bayesian network. And now we can see, we can check, do we have all the probabilities? So when I print this page, it didn't show all the probabilities, so they are the same. So I just copy and pasted a screenshot. So we need to store one value for y, so that's there. We need to store, given v is 1, we need to store only one value for a, because the probability of a being 0 given v is 1 is just 1 minus this, so it's 0.6. And similarly, given v is 0, the probability of a being 1, we have that number, so we can compute the other one. A being 0 is just 1 minus that, which is 0.65. So note that these two numbers indeed does not sum up to 1. They don't need to be. They don't need to sum up to 1. And so we have the same thing, 2 values for B and 2 values for C. So now we just need to compute this, and this, the first step is to add back all the values that are missing. So that's V being 0 and plus V being 1. So copy the X part, and then the Y part we need both possible values, either both 0 and 1. And then these things are called drawing probabilities. When we have that, then the formula is easy. Just take the multiples, just multiply, take the product of every variable given the parent. So in particular, the first term will be, what's the probability A is 0 given the parent V is 0. So given V is 0, A is 1, we know that, so we know the A0 is the other probability, 0.65. So again, we want the product of every variable given the parent, and here A has parent V and V is 0. So given V is 0, the probability of A being 0 is just 1 minus the probability of A is 1, which is 65. And then, of course, we do exactly the same thing. B is 1 given V is 0. We have that directly from the table. So that's 0.27. And the next one, C is 0 given V is 0. Where is it? So V is 0 is here. Given V is 0, C is 1, we know the probability. So C is 0 has probability 1 minus that. So that's 0.454. Again, 1 minus this number. So now we have the first term, and then we just add the other term. That term is A is 0 given V is 1, so it's 0.6. And then the second term is 0.96, we just copy that because B is 1. And then the last one is C is 0 given V is 1, so it's 0.7. Okay, and we're missing something. We're missing V given the parent. And we know that V does not have a parent because it's not naive Bayes. And V is 1 has probability 0.87, so we have that number here, and the other number, V being 0, has probability just 1 minus that, so it's 1, 3. So every time, remember to check there are 4 terms. Each term, again, is a probability given the parent, and you can find all of these numbers from the table. Okay, so the next question is, you have a Bayesian network, and now they are all binary variables, and again you are asked to compute the size of the conditional probability table. So the diagram is a bit large, but we can see it here. So starting from 0, we just need to store the probability of x0 being 0 and 1. We don't actually need it because the probability of x0 being 1 is just 1 minus the probability of x0 being 0 is probability of x0 being 1. So again, we do not need this, we just need one of them. So okay, so we have 1 here, and now this one. So this we need probability for the same reason we only care about the value x1 being 0, x1 being 1, we can compute from by 1 minus this thing. But the thing we're conditioning on is conditioning on the parent. So the parent is x0, so x0 can be 0 or 1. So there are two numbers to store here. And I think this question is kind of not that interesting. Let me actually add another branch so that it's slightly more interesting. Let's see. Let's just use red then. Okay, so suppose let's have another branch like this. Then for 2 is kind of the same as 0, so we need to only store one of them because there are no parents. We only need to store one conditional probability. And 3 has one parent, so 3 is similar to 1, so we need to store 2. And after we added this branch, then for 4 there are 2 parents. So in particular, we need probability of x4 is 0 given x1 and x3, and they can be equal to 0, 0, 0, 1, 1, 0, and 1, 1. And know that each one cannot be computed by the other ones, so because they sum up, these 4 numbers do not sum up to 1. So do not sum up to 1. So we need all 4 of them. And for each one, we just need one number here, because the other one, probability of x4 being 1, can be computed by 1 minus the probability of x4 being 0, given the same values for x1 and x3. So now we have 4 numbers here, and the 4 comes from 2 to the power 2. So if, say, 4 has 3 parents, then we need 2 to the power 3 number of conditional probabilities. Okay, so now we know for each variable how many conditional probabilities we need to store, so we can just add them up. So 1 plus 1 plus 2 plus 2 plus 4, so that's the total number of conditional probabilities we need to store in the CPT.